We are taking a 784-dimensional universe today.
Yeah, a space where, honestly, human geometric intuition just completely shatters.
Right, and we are violently crushing it down into a flat, readable map. Because, you just can't visualize 784 dimensions.
No, absolutely not.
Your brain evolved to understand 3 dimensions of space and 1 dimension of time. Anything beyond that, and our biological hardware just, well, it blue screens.
It completely crashes.
Exactly. But today, we are going to show you a mathematical trick that lets you see the invisible.
Welcome to the deep dive. And if you are tuning in right now, we know exactly who you are.
Oh, definitely do.
We are looking directly at the Bus and Sigma scholars of Edward Little High. We know you are an elite, hyper-curious crew, and we know you're ready to grind through the brutal, beautiful mechanics of complex data.
You're not here for the cliff notes.
Right. You don't just want the surface-level summary of how an algorithm works. You want the matrix. You want to look under the hood and understand the mathematical DNA. And we are pulling apart the entire engine today. The goal here is to traverse a very specific, incredibly elegant bridge in computer science.
As a long bridge, too.
It is. We're starting in the abstract philosophical realm of information theory, dealing with bits, probabilities, and the mathematical definition of surprise.
I love that word in this context. Surprise.
Right. And we're going to walk that forward, step by step, through cross-entropy and callback libular divergence until we arrive at the exact mechanics of t-SNE.
Which is t-distributed stochastic neighbor embedding.
Exactly. And it is arguably the most potent visualization tool in the history of machine learning.
And the hook for me, the thing that I haven't been able to stop thinking about since we went through the sources, is the cost of being wrong.
The penalty.
Yeah, the penalty. This entire algorithm, this magical ability to draw a map of 1,000 dimensions, is powered by measuring wasted bits of information. It builds a perfect map by strictly penalizing mistakes.
But to understand a wasted bit, we have to start at the absolute bedrock.
All right, before we can visualize data, before we can even talk about 784-dimensional space, we have to define the fundamental unit of data: information theory.
Claude Shannon, 1948. That is the genesis of all of this.
The absolute legend.
Truly. Shannon realized that information couldn't just be this vague qualitative idea. It couldn't be, how interesting a fact is or how much emotional meaning a sentence has.
He stripped all the human semantics away.
Completely. In the context of probability and statistics, Shannon rigorously defined information as the minimum number of bits required to encode an event. And it all revolves around one concept, which you mentioned: surprise.
I want to make sure we nail this, because when I first read it, it felt completely backwards to me.
How so?
Well, usually in just colloquial speech, if someone hands me a massive encyclopedia, I say, wow, that's a lot of information.
Sure, because it's a big physical book.
Right. But Shannon is saying that predictability actually destroys information. It's like predicting the weather.
Okay, let's use that.
If you predict that it's going to rain in the middle of the Sahara Desert and it actually rains, that is a massive surprise.
Huge surprise.
It's an incredibly rare, low probability event. So when it happens, you've gained a massive amount of information.
You've learned something genuinely new about the universe.
Exactly. But if you predict it's going to rain in a tropical rainforest during the monsoon season,
the probability is near 100%.
right, the surprise is basically zero. You haven't learned anything new.
That is the perfect intuition for this. Information is inversely proportional to probability. If I tell you the sun rose this morning, I have transmitted 0 bits of information to you because your uncertainty before I spoke was already 0.
You already knew it was going to happen.
Right. Mathematically, Shannon defined the self-information or surprise of a specific event as the negative logarithm base 2 of the probability of that event.
Let me stop you right there, because I want the Sigma scholars to actually visualize the math. Why a logarithm and why base 2?
Base 2 is simply because we are dealing with digital systems, binary states. A bit is a binary digit.
A 1 or a 0.
Exactly. It represents a choice between 2 equally likely outcomes. The logarithm is there because information needs to be additive.
Additive. Okay, break that down.
Let's say you flip a fair coin once. The probability of heads is 0.5. The negative log base 2 of 0.5 is exactly 1.
Okay, so you get 1 bit of information.
Yes. You asked one yes or no question, and your uncertainty was halved.
Right, and if I flip 2 fair coins, the probability of getting 2 heads is 0.25. and the negative log base 2 of 0.25 is 2.
Because you multiply the probabilities, but you add the bits.
So 2 independent coin flips give me 2 bits of information.
Precisely. The logarithm turns the multiplication probabilities into the addition of bits. It's a really neat trick.
It is, but here's where we transition from a single event to an entire system.
Right, because data sets aren't just one coin flick or one rainy day.
No, they are massive, complex probability distributions. We need a way to measure the total inherent uncertainty of the entire system.
And that measurement is called entropy. Specifically, Shannon entropy, denoted as H of P.
So if self-information is the surprise of one event, then entropy is just the average surprise.
A great way to put it.
You look at every possible thing that can happen in your data set, figure out how surprising each thing is, weight it by how often it actually occurs, and then average it all out.
It is the expected value of the information. If you have a true probability distribution P, the Shannon entropy H of P is the absolute theoretical minimum average number of bits you need to encode a message from that distribution.
It's a limit.
A hard limit set by the universe.
Let's test the extremes of that limit. If I have a two-headed coin, the probability of heads is 1.
Right, 100%.
So the log of 1 is 0, the surprise is 0. So the average surprise, the entropy, is 0.
The system is perfectly predictable. You need 0 bits to transmit the outcome because everyone already knows what's going to happen.
Okay, and on the opposite end, what kind of distribution maximizes entropy?
What do you think?
Well, it would have to be a scenario where you have absolutely no idea what's going to happen. Total randomness, a perfectly uniform distribution.
Yes.
If I roll a fair 20-sided die, every single face has the exact same probability. No single event is more expected than any other.
So every outcome is maximally surprising.
That is the state of maximum entropy.
And the practical reality of that is you cannot compress a truly random sequence of data because every single bit is a surprise. There are no patterns to exploit.
So H of P represents the ground floor.
Yes.
It is the inherent, unavoidable uncertainty of your true data. You cannot compress the data into fewer bits than the Shannon entropy without permanently destroying information.
Okay, so we've established the theoretical limit of perfection, the ground floor.
But in machine learning, we don't start with perfection.
No, we rarely ever achieve perfection.
We build models that try to guess the true distribution. We have reality, which we'll call distribution P, and we have our machine learning model's flawed approximation of reality, which we'll call distribution Q.
And what happens when Q doesn't match P?
When your model is wrong, you pay a tax.
A hefty tax.
You pay it in data storage, in computational inefficiency, in wasted effort. And to measure this tax, we need 2 new concepts, cross-entropy and callback-Leibler divergence, or just KL divergence for short.
Let's tackle cross-entropy first. The notation is H of P, comma Q, so it takes both distributions into account.
What is it actually calculating?
Cross-entropy calculates the total average number of bits it will take to encode data coming from the true distribution P. If you stubbornly and mistakenly use an encoding scheme that was optimized for your model Q.
I am using the wrong tool for the job.
Exactly.
And because my tool is based on a flawed assumption about reality, it's going to require more bits to get the job done.
Yes. But abstract math can be kind of slippery. To really anchor this for the students taking notes, we need to deploy a highly specific scenario.
Let's look at text compression.
Perfect.
I love this example from the sources. Let's build a data compression algorithm. Imagine I have a massive text document written in English. This document is my ground truth. It is distribution P.
Okay, distribution P is English.
Now, if I look at the true statistics of the English language, the letters E and T are everywhere. They are incredibly high probability. Meanwhile, Z and Q are very rare.
So if you were building a perfectly optimal encoding system, say, a Huffman tree, how would you assign your binary codes?
I'd be strategic. I would give the shortest possible bit codes, maybe just 0 or 10, to the letters E and T.
Because they show up the most.
Right, and I give long, chunky bit codes to Z and Q because I almost never have to use them. Over 1 million words, that strategy keeps my total file size incredibly tiny.
And if you did that perfectly, matching the true probabilities of English, your average bits per letter would exactly equal the Shannon entropy, H of P.
I would hit the theoretical minimum limit.
You'd be at the ground floor.
But what if my model is an idiot? Or, well, more accurately, what if my model was trained on the wrong data? Let's say my model, distribution Q, was trained purely on French literature.
Now the probabilities are totally warped.
How so?
In French, E is still common, but the letters A and S are significantly more frequent than they are in English, while T is much less frequent. Your French Model Q genuinely believes E and A deserve the absolute shortest bit codes.
It pushes T further down the list.
Exactly. It assigns T a much longer code.
So here's where the collision happens. I take my true English document, P, I feed it into my French compression software, Q.
And every single time the letter T appears in your English document, which is constantly, the software uses a longer bit code than it needed to.
My code is horribly inefficient.
The final file size just balloons. It becomes totally bloated.
And that total bloated file size, measured in average bits per letter, is the cross entropy H of P, Q.
It is the total cost of operating under a wrong assumption.
Okay, that makes perfect sense. The cross entropy is the bloated file size. So where does KL divergence fit into the picture? The sources refer to it as relative entropy, dKL of P parallel Q.
Right. If cross-entropy is the total bloated file size, KL divergence is strictly the bloat.
Just the extra part.
Yes, it is the exact number of extra, useless, wasted bits you had to spend solely because you used the French model instead of the optimal English model.
So it isolates the inefficiency.
Perfectly isolates it.
It is the pure mathematical penalty for being wrong.
Which brings us to the information identity. It is one of the most elegant equations in all of data science.
Hit me with it.
Cross entropy equals entropy plus KL divergence. H of P, Q equals H of P plus dKL of P parallel Q.
Let me map that back to the text example and make sure it really holds up. Total bloated file size equals the theoretical minimum file size plus the wasted bits.
That is exactly it. And there's a vital mathematical law governing this called Gibbs's inequality.
What does that state?
It proves that KL divergence is always non-negative. It is always greater than or equal to 0.
Meaning, you can never have a negative number of wasted bits.
Right.
You can't accidentally compress a file better than the Shannon limit by using the wrong model.
Yeah.
You can't stumble into being better than perfect.
No, the universe does not reward wrong assumptions with free data compression. The KL divergence only hits 0 in one specific scenario.
When distribution P and distribution Q are completely, perfectly identical.
When your model is reality.
I have a pushback here, though.
Okay, let's hear it.
If you look at the architecture of modern neural networks, if you look at the PyTorch or TensorFlow code that machine learning engineers write, they always use a cross-entropy loss function.
That's true.
They are constantly trying to minimize cross-entropy. But based on what we just walked through, isn't KL divergence the actual pure measurement of how wrong the model is?
Yeah.
Why are they targeting cross-entropy instead of directly targeting the wasted bits?
It looks like a contradiction, I know, but it's actually a brilliant computational shortcut.
Okay, walk me through it.
Let's look at the training environment of a neural network. You have a massive data set of images or text. That is your true distribution P. During training, does that true data set ever change?
No, the data is fixed. The images in the folder don't spontaneously change their pixels.
Exactly. Because the true dataset P is fixed, its inherent uncertainty, its Shannon entropy H of P, is a constant. It's a static number.
Okay, it doesn't move.
Let's say it's exactly 1.5 bits. It will never fluctuate. Now look at the equation again. Cross entropy equals a constant plus KL divergence.
Oh. Oh, I see it. It's basic algebra.
Yes.
If variable A equals a constant plus variable B, any mathematical operation you perform to shrink, variable A will automatically shrink variable B by the exact same amount.
Exactly. Imagine you are standing on a concrete block.
Yeah.
The height of the block is the Shannon entropy. Your total height from the floor to the top of your head is the cross entropy. The distance from the block to the top of your head is the KL divergence.
Okay, I'm visualizing this.
If you want to make yourself shorter, you can measure from the floor or you can measure from the block. The math works out exactly the same.
But why measure from the floor? Why is cross entropy preferred by the computer?
Because calculating the absolute Shannon entropy of a massive, continuous, high-dimensional data set is computationally agonizing.
Really hard to do.
It requires integrating over incredibly complex spaces. It would take forever. But the formula for cross entropy is comparatively very simple to compute.
So engineers tell the computer to minimize cross entropy, knowing with absolute mathematical certainty that they are simultaneously driving the KL divergence down to 0.
Yes. They're squeezing the wasted bits out of the model without having to calculate the constant baseline.
That is incredibly satisfying.
Brilliant.
So we now have a mechanism to violently penalize a model for being wrong using wasted bits.
We do.
But the stated goal of this deep dive is visualization. How does compressing French text or measuring wasted bits help me draw a map of a 784-dimensional dataset? What is the connection?
The connection arises from a crisis. In data science, there is a phenomenon known as the curse of dimensionality.
The curse of dimensionality.
It is the terrifying realization that human intuition and classical geometry completely break down in high-dimensional spaces.
I think we need to linger on this because it's hard to even conceptualize 100 dimensions, let alone 784. How does geometry break down? A triangle is still a triangle, isn't it?
Well, let's look at distance and volume. Imagine a circle perfectly inscribed inside a square, so the edges of the circle just touch the sides of the square.
Okay, I can picture that.
In two-dimensional space, the circle takes up most of the area of the square. Roughly 79% of the space is inside the circle.
Right, there are just those 4 little empty corners left over.
Now step up to three-dimensional space. A perfect sphere inscribed inside a cubic box.
Like a basketball in a shipping box.
Yes. The sphere still takes up a lot of the volume, about 52%, but notice the trend. The corners of the cube are getting larger, and the sphere is taking up less of the total space.
Okay, I followed the trend. 52% is a big drop from 79.
Now extrapolate that math into 100 dimensions, or 784 dimensions. As the number of dimensions increases, the ratio of the volume of the hypersphere to the volume of the hypercube asymptotically approaches 0.
Wait, the sphere disappears.
Effectively, yes. The volume of the sphere becomes infinitesimally small compared to the cube.
That is wild.
This means that in high-dimensional space, almost all of the volume of a hypercube is located out in its infinitely spiky corners. The center is virtually empty.
That is deeply unsettling. It's like a galaxy where the core is completely hollow and all the stars are pushed out to these sharp, distant edges.
And because everything is pushed out to the corners, the traditional concept of Euclidean distance, taking a straight ruler and measuring the gap between point A and point B, becomes totally meaningless.
Why?
Because in high-dimensional space, every point is incredibly far away from every other point. The distances between points become almost uniform. A ruler cannot tell you who is close to whom because everyone is light years apart.
If distance is broken, how can we possibly group similar data points together to draw a map? If the ruler fails, what do we use?
This was the breakthrough achieved by Geoffrey Hinton and Sam Royce when they invented t-SNE stochastic neighbor embedding.
Okay.
They realized that you cannot rely on physical distance. Instead, you have to preserve neighborhood identities as probabilities.
We are abandoning geometry and moving back to probability.
Yes.
How does SNE define a neighborhood?
Imagine you pick a single data point in that terrifying, mostly empty 784-dimensional space. t-SNE drops a Gaussian distribution, a multidimensional bell curve, centered perfectly on that point.
Okay, a bell curve over a point.
Then it looks at all the other thousands of points in the space.
And the Gaussian curve dictates the relationship.
Exactly. The closer another point is to the peak of that bell curve, the higher the probability that they are neighbors. If a point is far away, out in the tail of the bell curve, the probability approaches 0.
Okay.
We call this high-dimensional probability Pij. It is the probability that point I would pick point J as its neighbor.
So instead of saying point A is exactly 5.2 units away from point B, t-SNE says there is a 95% chance that point A considers point B to be its neighbor. We've turned a physical Euclidean distance into a probabilistic measure of friendship.
And now the algorithm creates a blank, two-dimensional canvas, the map we want to draw.
Right.
It scatters points randomly on this flat map, it drops bell curves on these 2D points, and calculates a new set of probabilities, which we call Qij.
I see the architecture now. We have a true probability distribution in the high-dimensional space, P, and we have a model probability distribution on our 2D map, Q.
We are right back to information theory.
We want the map's neighborhoods, Q, to perfectly mimic the high-dimensional true neighborhoods, P. How do we measure the difference between two probability distributions and penalize the model for being wrong?
We calculate the KL divergence.
We measure the wasted bits. t-SNE wants to move the points on the 2D map around until the KL divergence between P and Q is as close to 0 as possible.
Exactly. t-SNE minimizes the sum of the KL divergences over all data points. But this is where we have to look closely at the specific mathematical quirks of KL divergence.
It's not just a straightforward penalty, is it?
No, it is not a simple uniform ruler. We established earlier that it is a strict penalty. What we haven't discussed is that KL divergence is highly asymmetric.
Asymmetric, meaning dkl of p parallel q does not yield the same number as dkl of q parallel p.
Precisely. Because of how the probability fractions interact with the logarithm in the formula, KL divergence weighs different types of spatial errors very differently.
Let's break down the types of errors.
Okay, let's look at the first type of error. Suppose Pij is very large. In the true 784-dimensional data, these 2 points are incredibly similar. They are best friends.
Got it. Large p.
But suppose your 2D map makes a mistake. It drops them on opposite sides of the canvas, making Qij very small.
So large p and a small q.
When you plug a massive p and a tiny q into the formula, you are multiplying a large number by the logarithm of a massive ratio. The KL penalty explodes.
It's a massive spike in wasted bits.
The algorithm screams at you. It heavily penalizes tearing best friends apart. It acts like a massive rubber band, violently pulling those points back together on the map.
Yes. Okay, now let's look at the second type of error. Suppose Pij is incredibly small.
In the high-dimensional reality, these 2 points are totally dissimilar. They are complete strangers.
Small p.
But your 2D map accidentally places them right next to each other, making Qij very large. What happens to the math?
If p is tiny, say 0.0001, and it's sitting on the outside of the logarithm multiplying everything else, it's going to crush the final number, regardless of what's inside the log.
Exactly.
The penalty is going to be virtually zero.
The algorithm looks at this mistake, squishing complete strangers together, and essentially says, I don't care. The penalty barely registers.
I love this. It's like a hyper-strict seating chart at a Sigma Scholar lunch table.
Oh, that's a good way to picture it.
The SNE algorithm is the teacher monitoring the room. If the teacher sees you separate 2 best friends, large P, small q, you get an instant detention. The penalty is huge.
Right.
But if the teacher accidentally seats 2 complete strangers right next to each other at the end of the table, small p, large q, they barely notice. No penalty. The algorithm is obsessed with preserving local structure and completely apathetic about global structure.
It ruthlessly prioritizes local neighborhoods.
But wait, think about the physical consequences of that on a map. If the algorithm violently pulls friends together, but exerts almost zero penalty for squishing strangers together, won't the map just collapse?
What do you mean?
Well, if there's nothing pushing the strangers apart, wouldn't all the data points just pile up in a massive traffic jam in the center of the canvas?
You have just independently diagnosed the fatal flaw of the original SNE algorithm. You have arrived at what researchers call the crowding problem.
Walk me through the mechanics of the crowding problem, because this seems like an unfixable geometric issue.
It is a geometric issue. Remember the hypersphere and the hypercube. In a high-dimensional space, say 10 dimensions, there is an enormous amount of mathematical room for points to be moderately far apart from each other.
Think of the corners.
Right. You can have a center point and a dozen points equidistant from it, all sitting in different orthogonal corners.
Right, there is infinite room to spread out without running into anyone else.
But when you crush that data down to a flat 2D screen, you only have an X and a Y axis. You don't have enough physical area to accommodate all those moderate distances. The 2D map literally runs out of real estate.
So what does the algorithm do?
Well, to keep the best friends together, which we know SNE violently demands to avoid that massive KL penalty, it ends up having to push moderately distant points much, much farther away on the map.
Because it's frantically trying to make room on a flat surface.
Yes. But in pushing those moderate points far away, it triggers a chain reaction, it runs out of space at the edges, and it ends up squishing everything else into a single, giant, overlapping blob in the center.
Because there is no strong KL penalty for squishing strangers together.
Exactly. The distinct clusters collapse into a traffic jam. The visualization becomes a useless smear.
SNE fails. It preserves local friends, but completely ruins the global map. The map is unreadable. So how do we clear the traffic jam?
This is where Lawrence van der Maten and Jeffrey Hinton introduced the revolution. They published a paper detailing a solution called t-SNE.
And the T stands for what?
It stands for the student's T distribution. They realized that the KL divergence penalty wasn't the core issue. The issue was the Gaussian bell curve they were using to calculate probabilities on the 2D map.
Okay, so they rip out the Gaussian bell curve on the 2D canvas and they swap it for a t-distribution. Why? What is the mathematical difference between those two curves?
Specifically, they used a student's t-distribution with 1 degree of freedom, which is mathematically identical to a Cauchy kernel.
Okay, a Cauchy kernel.
The crucial transformative difference between a Gaussian distribution and a Cauchy distribution is the shape of their tails. The edges of the bell curve as it slopes down toward the horizontal axis.
The tails. Let's contrast them.
Well, a Gaussian distribution, it has what we call an exponential decay.
Okay, exponential.
Right. The formula literally includes e's raised to a negative power based on the squared distance. Because it's exponential, the curve drops off to 0 incredibly aggressively.
So it drops fast.
Incredibly fast. I mean, aggressively fast. By the time you move just a moderate distance away from the center of that curve, the probability is effectively, it's just 0.
So under a Gaussian, if you move slightly away from a point, you are instantly dead to them. You are no longer a neighbor.
Exactly. But the Cauchy distribution, the t-distribution they swapped in, uses an algebraic decay. Its formula is essentially 1 over the quantity 1 plus the squared distance.
It does not use the exponential functioning.
Right. Because of this algebraic decay, it possesses what statisticians call heavy tails.
Heavy tails. What does that literally look like if I draw it on a chalkboard?
It means the curve doesn't swoop down and crush itself against the 0 line immediately. It stays slightly elevated. It hovers above the horizontal axis thicker and fatter as it stretches out to infinity.
Oh, I see.
Because the tail is heavy, it assigns a relatively higher probability to points that are physically very far apart.
I am trying to connect this mathematical shape back to the map and the traffic jam.
Yeah.
If the heavy tail gives a higher probability to things that are far apart, how does that stop the crowding?
Think about the KL divergence penalty again. The algorithm needs the 2D map probability, Q, to match the high-dimensional probability, P.
Okay.
If you use a Gaussian and you push 2 points slightly far apart on the 2D map to make room, the Gaussian probability drops to 0 instantly. Q becomes 0, and the KL penalty explodes.
I see.
With the Gaussian, you are trapped. You can't make room without triggering the alarm.
But with the heavy-tailed Cauchy distribution, you can push 2 points much, much farther apart physically on the 2D canvas. And because the tail is hovering above the axis, the formula still assigns them a decent, non-zero probability Q.
Exactly. The heavy tails essentially lie to the KL divergence. They buy the algorithm extra geometric space. It allows the algorithm to push moderately dissimilar points much further away from each other on the 2D map without triggering a massive penalty.
It gives the distinct clusters physical room to breathe.
The algorithm is basically saying, you can move far away, but my heavy tail still touches you, so mathematically we are still neighbors enough to satisfy the penalty.
It is a profound mathematical trick. The traffic jam clears up and the clusters separate beautifully.
Now, Vandermont and Hinton also added one more crucial fix to the mathematics, a concept called symmetrization.
Symmetrization. What was wrong before?
In the original SNE, the probability that point A chose point B as a neighbor wasn't necessarily the exact same as the probability that B chose A.
Like unrequited friendship. Point A is in a sparse area, so it reaches out and thinks B is its best friend. But B is in a dense area surrounded by closer points, so it thinks A is just an acquaintance.
Right. The conditional probabilities, Pi given J and Pj given I, were asymmetric. This caused massive optimization headaches for the computer. So in t-SNE, they simply compute the joint probabilities by averaging the two conditional probabilities together.
Okay, averaging them.
Pij is defined mathematically as the sum of Pi given J and Pj given I divided by 2n. So the probability of A and B is strictly equal to the probability of B and A.
It forces the relationships to be reciprocal.
It does more than just clean up the math. This symmetrization ensures that every single data point, even massive outliers floating out in the high-dimensional void, contributes meaningfully to the overall cost function.
Why wouldn't it otherwise?
Without it, an outlier point that nobody wanted as a neighbor would have a p-value near 0 for everything, meaning its KL penalty would be 0 everywhere. The algorithm would just abandon it.
You would get lost in the map.
Yes. Symmetrization ensures no point is left behind. Every single point gets a say in how the final map is drawn.
Okay, this is a beautiful theoretical framework. We have the asymmetric KL divergence to ruthlessly preserve friends. We have the symmetric probability so nobody gets abandoned. And we have the heavy-tailed t-distribution to artificially inflate the 2D space and cure the crowding problem.
It's all all coming together.
But how does the computer actually execute this? How does it physically move thousands of points around a screen to minimize this complex KL divergence equation?
It relies on an optimization technique called gradient descent. But the brilliance of t-SNE is that its gradient descent behaves exactly like a physical simulation. It uses the laws of physics.
This sounds like the perfect moment to break out our second major visualization tool, the n-body spring analogy.
Let's do it.
If I'm programming this on my computer, what is the engine actually doing?
Imagine you take your data set, let's say 6,000 individual data points, and you throw them completely randomly onto a blank 2D screen. It just looks like TV static.
Complete chaos.
Now, imagine that every single point on that screen is connected to every other single point by a magical, invisible spring.
So if I have 6,000 points, there are millions of invisible springs crisscrossing this map.
Exactly. Millions of them. Now, we need to calculate the gradient of the KL divergence. The gradient is simply the vector calculus telling us which direction we need to move every point and how fast to lower the number of wasted bits.
Okay, vector calculus.
Remarkably, when you derive the mathematical formula for the gradient of t-SNE, the equation literally mirrors a physical force equation from classical mechanics.
It acts like Hooke's law. Force equals negative k times the displacement.
Yes. The math translates perfectly to physical springs. And these springs exert two specific types of forces dictated by the probabilities we calculated. Let's look at the attractive force first.
Okay, attraction.
If 2 points were highly similar in the high-dimensional space, meaning Pij is very large, the spring connecting them on the 2D map becomes incredibly tense and highly compressed. It exerts a powerful attractive force.
So the best friends are getting violently yanked across the map toward each other.
Yes. But what about the strangers? The equation also produces a repulsive force. If 2 points were dissimilar in the high-dimensional space, the heavy-tailed Cauchy distribution on the 2D map causes their spring to push outward.
Okay.
The spring exerts a repulsive force, trying to shove the points away from each other.
So gradient descent is just letting this physics engine run. The computer calculates the millions of pulling and pushing forces. It moves every point a tiny millimeter, then it pauses.
It recalculates everything.
It recalculates all the new angles and forces, moves them again, and iterates hundreds of times until the springs settle into a stable, low-energy equilibrium.
That is the literal mechanism. But if you just unleash that raw physics simulation, you run into a mechanical problem. Imagine all these points pulling and pushing randomly. It's very easy for a cluster of points to get trapped on the wrong side of the map, blocked by a wall of repulsive forces from another cluster.
Like they're stuck behind enemy lines.
Exactly, they get stuck in a local minimum. To prevent this, the algorithm uses a very clever trick during the first few seconds of the simulation called early exaggeration.
Early exaggeration. What force is it exaggerating?
For the first 50 to 100 iterations of the simulation, the algorithm artificially takes all the attractive forces, all the Pij values, and multiplies them by a large number, usually around 12.
It turns the gravity up to 12. Why would you want to do that?
Because it forces all the similar points to aggressively and instantly snap together into incredibly tight, dense little microclusters. All the distinct groups form immediately into these hard nuggets.
Oh, wow.
Because they are crushed so tightly together, there is suddenly a vast amount of empty space on the 2D map.
Oh. Because there is empty space, these tight little nuggets can freely float past one another, navigating the repulsive forces until they find their proper global arrangement on the canvas without getting tangled up.
It's exactly like planet formation in an early solar system. Once the clusters have found their correct neighborhoods, the algorithm turns off the early exaggeration.
The multiplier drops back to 1.
The extreme gravity relaxes, and the tight little planetary clusters expand and breathe out into their final natural shapes.
That is just phenomenal engineering. Now, there is one parameter in t-SNE that I see in every Python library, and the human user actually has to type it in before they run the algorithm. It's called perplexity. What exactly is this tuning knob doing to our springs?
Perplexity is the master control knob, and it dictates everything about how the final map looks. We touched on it briefly when we discussed the original high-dimensional Gaussian distributions.
Remind me.
Perplexity is mathematically defined as 2 raised to the power of the Shannon entropy of the local distribution. Conceptually, it is a smooth measure of the effective number of neighbors each point has.
Effective number of neighbors. So if I set the perplexity to 30 in my code, I'm telling the algorithm, hey, I want you to focus on the 30 closest friends for every single point.
Roughly speaking, yes. What the algorithm actually does mechanically with that number is adjust the variance, the width of the high-dimensional Gaussian bell curve for every individual point dynamically.
Dynamically. So the initial bell curves aren't all the exact same size.
No, and they can't be, because real data is clumpy. Some regions of your high-dimensional space will be incredibly dense, packed with hundreds of points. If a data point is in one of those dense regions, the algorithm forcefully shrinks its bell curve so it only encompasses the target perplexity, say, 30 neighbors.
Okay, that makes sense for dense areas.
But if a data point is floating out in a sparse, empty void, the algorithm inflates its bell curve massively, reaching out across the void to find enough neighbors to hit that exact same target perplexity.
It forces a mathematical equity. It ensures every point gets the exact same amount of neighborhood attention, regardless of how crowded their specific reality is.
Yes.
How does changing that target number impact the visual map we see at the end?
It changes the entire topological scale. If you set the perplexity to an extreme low, say 2, the algorithm becomes hyper-focused on extreme local pairings. The visual impact is that the data shatters.
Chatters.
Your map turns into thousands of meaningless, tiny pairs of dots, completely isolated from everything else. You lose all the big picture macro structure.
The algorithm is too obsessed with individual best friends to see the community. What if I dial it up to 50?
A perplexity somewhere between 30 and 50 is widely considered the sweet spot for most datasets. It forces the algorithm to consider a broader neighborhood, balancing the strong local pull of best friends with the gentle gravitational pull of the wider community. This is where you see those beautiful, distinct, meaningful clusters form.
And if I crank it up to 500?
The bell curves become so incredibly wide that almost everyone is considered a neighbor with everyone else. The attractive forces overwhelm the map, and the data just collapses into a single, dense, unstructured blob. You lose all local nuance.
So perplexity is literally the master knob for tuning the focal length of the algorithmic lens, moving your view from microscopic to macroscopic.
Perfectly said.
Okay, we have spent enough time theorizing. We have built the engine, we have the bits, the Shannon entropy, the asymmetric Hale divergence, the heavy-tailed Cauchy physics, and the perplexity tuning knob.
It is time to turn the key.
It is time to unleash this machinery on reality. This brings us to the ultimate test case, our third required exploration, the MNIST masterclass.
MNIST is legendary. It stands for the Modified National Institute of Standards and Technology Database. In the realm of machine learning and computer vision, it is the equivalent of Hello World.
What exactly is the data?
It consists of tens of thousands of images of handwritten digits, the numbers 0 through 9. These were originally collected from high school students and Census Bureau employees. For our t-SNE example, we typically take a subset of about 6,000 images to run the algorithm on.
Okay, 6,000 images of handwritten numbers. How complex is this mathematically?
Each image is a grid of 28 by 28 pixels, rendered in grayscale. If you unroll that 2D image grid into a single continuous line of pixels, 28 times 28 equals 784.
And there it is, the 784 dimensions we started the show with. So, mathematically, each individual handwritten number is not a picture. It is a single coordinate point existing in a 784-dimensional space. The coordinates are just the darkness values of the 784 pixels.
Yes, 784 dimensions of pure, unvisualizable chaos. If you try to use older classical linear techniques to map this data down to a 2D screen, the results are disastrous.
Let's look at the failure state first. If we use PCA, principal component analysis, what does the map look like?
PCA is a linear projection. It tries to preserve global variance, essentially rotating the high-dimensional data and shining a light on it to cast a 2D shadow. When you project the MNIST data using PCA, the output on the graph just looks like a massive, overlapping, rainbow-colored cloud.
Just a mess.
The zeros are completely smeared into the sixes, the nines overlap the fours. There is no separation. It's a chaotic mess. Even early nonlinear methods like salmon mapping fail to cleanly separate the classes. They just create a giant sticky ball where only a few extreme edges are distinct.
But when we apply t-SNE, when we calculate the high-dimensional Gaussian probabilities, initialize the 2D canvas, connect the millions of invisible springs, fire up the early exaggeration gravity multiplier, and let the heavy-tailed Cauchy physics simulation run to equilibrium what emerges on the screen.
The transformation is truly breathtaking. You watch the chaotic cloud literally shatter. The invisible springs pull and push with mathematical precision until the data self-organizes into distinct, isolated islands on the screen.
Wow.
All the handwritten zeros, thousands of them, written by different people with different handwriting styles, fly across the 784-dimensional space and pull together into a single, beautifully cohesive island on the 2D map.
And the ones form another island, and the twos form another. The digits are perfectly separated by vast, empty oceans of white space. And here's the truly staggering part. The algorithm was never told what a 0 or a 1 is.
No, it has no concept of numbers.
It simply discovers the underlying geometric truth of human handwriting purely by minimizing wasted bits of information.
And it gets even deeper than that. This is where the exquisite sensitivity of t-SNE truly shines. Because it is so violently protective of local topological structure, it doesn't just cluster the numbers, it clusters the microfeatures within the islands.
Give me an example of a microfeature.
Take the island of the digit 2. If you zoom in on that specific island on the map, you will see that t-SNE has grouped all the loopy 2s, the ones where people draw an extravagant cursive loop at the bottom base on one specific side of the island.
Okay, and the others?
And it has placed all the slanted, sharp-cornered 2s on the complete opposite side of the island.
It clustered the handwriting styles. It found the cursive typography naturally.
Yes. Or look at the island of 7s. In Europe, people frequently write a 7 with a horizontal line crossed through the middle vertical stem. In America, they usually just draw 2 lines.
Right.
In the t-SNE map, the continental class 7s form a distinct, tight subcluster completely physically separated from the standard 7s within the main island. The algorithm discovers the subtle variations in human culture just by analyzing the pixel distances and minimizing KL divergence.
That is just mind-blowing. It's like it sequenced the DNA of the handwriting.
Yeah.
Now, seeing results like that, seeing that level of magical clarity, the immediate temptation for any young data scientist is to say, this is the God algorithm. I'm going to throw away PCA, I'm going to throw away everything else, and I'm just going to use t-SNE for every data set I ever encounter for the rest of my life.
And that temptation is exactly why so many data scientists end up publishing deeply flawed papers. We have to discuss the critical caveats of t-SNE. It is a visualization tool. It is an incredibly powerful way to explore data, but it is not an absolute geometric map, and it is absolutely not a predictive model.
Wait, what do you mean it's not a geometric map? We just spent 15 minutes talking in vivid detail about islands, oceans, and subclusters based on geometry.
We have to remember the perplexity tuning knob. Remember how we said the algorithm dynamically shrinks the bell curve in highly dense areas and artificially inflates it in sparse areas, just so every single point has the same effective number of neighbors?
Yes, the dynamic mathematical equity.
Because the algorithm intentionally and aggressively warps the local density to balance the map, the visual size of a cluster on a t-SNE plot means absolutely nothing about the actual physical density of the data in the true high-dimensional space.
Oh, wow. So if I look at my map and I see a giant, sprawling, massive island of zeros and a tiny, incredibly dense pinpoint island of ones, I cannot conclude that the ones are more tightly packed in reality.
Correct. That conclusion would be scientifically fraudulent. The algorithm intentionally inflates the dense clusters and compresses the sparse ones to make the final visualization readable on your screen. Furthermore, the empty distances between the distinct islands also mean very little.
Why? If the island of zeros is 2 inches away from the ones, but 5 inches away from the nines, doesn't that mean zeros are closer to ones?
Not necessarily. Remember, the algorithm uses a heavy-tailed Cauchy distribution to ignore large distances. It barely penalizes squishing strangers together, and it freely pushes clusters far apart just to make room. The global geometry is highly distorted to preserve the local geometry.
So the golden rule is never, ever use a physical ruler on a t-SNE map. You can trust the local neighborhoods, but you cannot trust the global distances or the sizes.
Never use a ruler.
Okay, that addresses the map issue. But what about prediction? If I have a massive data set of medical patient records, and t-SNE perfectly separates the healthy patients from the sick patients, why can't I use this map as a predictive model when a new patient walks into the hospital?
Because t-SNE is a non-parametric embedding. It does not learn a universal mathematical function that maps input X to output Y. It strictly learns the exact specific resting positions of the specific 6,000 points you fed it during the simulation.
So if a 6,000 first image of a number arrives, or a new patient arrives,
Right.
I can't just plug them into an equation and plot them on the screen.
No, there is no equation for new data. To add a new point, you would have to insert it into the void, magically connect it with thousands of invisible springs to all the original 6,000 points, calculate the gradients, and run the entire immense physics simulation over again to find its resting place. It is completely computationally unfeasible for live prediction.
It's a bespoke suit. It is perfectly, flawlessly tailored exactly to the data you already have, but you can't just slip it onto a new person. It is strictly an exploratory tool to help humans generate hypotheses.
Precisely. You use t-SNE to see if the structure exists. Once you confirm the structure is there, you switch to a proper predictive algorithm, like a neural network or a random forest, to actually perform the classification.
Wow. Okay, Boson Sigma scholars, let's take a breath and bring this monumental journey full circle.
We have covered a vast amount of intellectual territory.
We started the absolute foundation with Claude Shannon and the sheer probability of surprise. We learned that information is strictly measured in binary bits, and the inherent, unavoidable uncertainty of reality is the Shannon entropy.
We then explored the cost of being wrong. We used the French and English text compression example to understand how a flawed model demands extra bits. This gave us cross-entropy as the total bloat-in cost and KL divergence as the razor-sharp measure of the wasted bits. We learned the elegant algebraic shortcut that minimizing cross-entropy mathematically guarantees you're minimizing the KL divergence.
Then we crashed into the curse of dimensionality, a space where hyperspheres vanish into corners and Euclidean distances become meaningless. We saw how SNE solved this by converting physical distances into Gaussian probabilities of friendship, using the asymmetric penalty of KL divergence to ruthlessly protect local neighborhoods.
Which directly led to the traffic jam, the crowding problem. Because a flat 2D canvas simply does not have the volume to host high-dimensional relationships without crushing points together.
And we witnessed the t-SNE revolution. By ripping out the Gaussian curve and swapping in a heavy-tailed Cauchy-T distribution, we gave the algorithm extra space. We watched the gradient descent unfold with our n-body spring analogy, using early exaggeration to forcefully form tight planets, and perplexity to masterfully tune the focus.
And finally, we saw it conquer the 784 dimensions of the MNIST dataset, shattering the chaotic cloud into beautiful, distinct islands of handwritten digits, right down to the cursive typography. All while remembering the strict caveats, it is an exploratory tool, and you can never measure density or global distance on the final map.
It truly is a masterclass in how layers of abstract mathematics, bits, divergence, asymmetric penalties, heavy tails, and simulated physics can combine to literally render the invisible matrix of high-dimensional data fully visible to the human eye.
It is, without a doubt, one of the most elegant mathematical achievements in modern data science.
But of course, on the deep dive, we never want to leave you completely comfortable. We don't want you to think the science is settled. We like to leave our Sigma scholars with a splinter in their minds. A new, entirely unresolved paradox to chew on.
Ah, yes, the uniform scale paradox. This is something actively debated in the literature right now.
Right. So we've spent an hour talking extensively about how KL divergence is the fundamental engine, the absolute mathematical judge, measuring the quality of our t-SNE map. Minimizing KL divergence means minimizing wasted bits, and the lowest number gives us the objectively best map. But recent research has uncovered something deeply fundamentally weird about KL divergence when applied to these embeddings.
It turns out that the KL divergence metric is highly scale sensitive.
What does that actually mean mechanically? Imagine you run your t-SNE algorithm on the MNIST data, and you get a beautiful, perfect map of the islands. The KL divergence has hit a perfect minimum. Now imagine you just uniformly scale that entire map up. You don't change the relative positions of any points. You don't move the clusters closer or further apart relative to each other. You literally just take the map, put it on a photocopier, and blow it up to 200% size. The physical canvas is larger, but the relative relationships are perfectly mathematically identical.
The topological structure hasn't changed a single degree.
Exactly. But if you run the math and recalculate the KL divergence on that larger photocopied map, the value changes. The number of wasted bits is suddenly completely different, even though the data's relationships are completely identical, just drawn on a bigger piece of paper.
Which is deeply unsettling for researchers who rely on this metric as an absolute truth.
So here is our final challenge for the Sigma scholars to research, debate, and grind on their own. If the foundational metric of our entire visualization technique, the almighty KL divergence, changes its mathematical value simply by zooming in or out on the map, how can we mathematically trust it to compare the quality of embeddings across completely different data sets? If scale breaks the metric, what does that mean for the maps we are trusting to guide us through the high-dimensional dark? A phenomenal, open question to ponder. Thank you for joining us in the Diagnostic Muddy Waters. Keep grinding through the data, stay curious, and we'll see you on the next deep dive.